So welcome to this sixth lecture now on optical microscopy. What we will do today is we'll review some of the properties of Fourier transforms. And we're not so interested in being able to do all the maths associated with Fourier transforms, just enough so we understand how to use the results properly and how to interpret what we might see in a microscope, which we have in the last lecture seen performs Fourier transforms for us. So between the sample plane and the back focal plane of the objectives, these are two conjugate planes, and actually it turns out that one plane is the Fourier transform, contains the Fourier transform of the other plane. So that's how we can think about this. So we form one Fourier transform going from the sample plane to the back focal plane of the objective, and then so essentially what we do in this part is we analyze the content of the sample in frequency space, if you so want. You will see what that means after this lecture. And then, so this is called analysis, Fourier analysis. And then what the tube lens then does, it takes these spectral components, these spatial frequencies that appear in the back focal plane of the objective, and it synthesizes the image information with it. So this is a Fourier synthesis program, so operation. So we have two Fourier transforms. We have an analysis part and a synthesis part. That's how you can think of the imaging process inside the microscope. So here we step back a bit and just look at Fourier transforms and how they come about. And once we have that, we have all the tools we need for this course. So with that, I'll switch again to the projector, and I'll begin with the key concepts. We saw that in the Fraunhofer limit, the diffraction integral looks like a Fourier transform, and we will take home that the Fourier transform of a function yields its so-called frequency spectrum. We will think always in terms of real space and frequency space when we talk about microscopes. And the imaging system, the conjugate planes tell you how you go from one space to the other, from real space to frequency space, and then from frequency space back to real space. The Fraunhofer diffraction pattern, as we know, is the Fourier transform of the aperture function, and the key concept for this lecture is that any function can be synthesized from a sum of harmonic functions. And this is the work of an important man called Joseph Fourier, who was one of the most important scientists in Napoleon's time, and he was a mathematical genius, of course, and incredibly gifted in lots of different things, a super engineer, super mathematician, and so it's a remarkably useful concept that is used in science all over. So the key aspects of Fourier synthesis are that any periodic function can be represented as a sum of orthogonal harmonic functions. So what that means is these are functions. So let me just go into this. The Fourier synthesis. If you have so orthogonal harmonic functions are functions of the form, for example, sine kx, cos kx, e to the I kx, etc. And orthogonality means that the integral over one period between minus pi and pi of two functions. So x times e to the minus I k b x is equal to 2 pi delta a b, and that is equal to 2 pi for a equals b and 0 otherwise. So for example, if you take the integral of e to the I 2x times e to the minus I 3x, then for between minus pi and pi, then that is equal to 0, because so these two functions are orthogonal. So if you work that out, that integral, you get 0. Similarly, if you have e to the I 2x times e to the minus I 2x, that turns out to be delta. So that's obviously 1 when you do that dx, and if you so what you end up with is this ends up to be 2 pi for this function here. Okay, and so if I have such an orthogonal set of periodic functions, then I can get any other periodic function. Any other periodic function can be synthesized by components plus sum k equals minus infinity to infinity ck e to the I kx. And so these are harmonic components, like sine waves. And these are the amplitudes of each component. And k is equal to 1, 2, and so on. These are integers in this case. And so any periodic function can be synthesized by these harmonic components. So you could even say that you know, a C0 is essentially the zero frequency of this. So these are frequency components. These are the amplitudes. That's the DC term in this case. So just to give you an example, so just to make sure, orthogonality means that any two functions minus pi to pi g of x times h dashed of x dx equals 0, that means they're orthogonal, right? So so for example, we can take a full set of cosines, cosine x, cosine 2x, cosine 3x, and so on, from minus infinity to infinity, so cos kx with k ranging from minus infinity to infinity, and using all those to synthesize any other periodic function to do that. So here you have one example which I show you. So you have two functions, 3 sine 2x plus 5 sine 5x. Sine 2x and sine 5x are definitely orthogonal, so that the integral of this would be 0 for these two components. So if you add these two components up, so you see underneath, I'll just draw this in. This is a slow frequency, so it will be that's the sine wave. Sine 2x goes through 0 like that, and then there's the other sine wave 5x, which is oscillating much faster. You can see that here. And so if I take the sum of those two, I get a new periodic function that contains these two components. So you can see, of course, if I add this red point here with the function of this value here, I get something that's more negative. So that's this blue point. So the minimum will be somewhere down here. There both functions are 0, so you get 0 also in this new periodic function. So GP is essentially, so this is what that function looks like. And it doesn't matter what periodic function you can think of, i.e. one that repeats over after each period, the function repeats. Any function can be represented as a synthesis like this as a, so this is called Fourier synthesis. So just to say this, that these terms e to the I kx are called the harmonic components, or we will talk about these as the spectral components, and they have frequency k, and each one is weighted with the right amplitudes. Okay, so right. The opposite operation is called Fourier synthesis. So in Fourier analysis, essentially, Fourier analysis. We've had Fourier synthesis already, but Fourier analysis is the other operation. Fourier synthesis is taking harmonic components, taking the right amplitudes and the right frequencies, and adding them up. And Fourier analysis is actually is the process of finding these amplitudes, ck. Let's suppose you have a periodic function, any periodic function. So the Fourier analysis part is trying to find out what are the amplitudes of individual frequency components. What is the spectrum, we say? What is the spectrum? What are the spectral components in this periodic function? And the way you get this, so if you write again, the synthesis part, any periodic function, is C0 plus sum minus infinity to infinity components times this orthogonal set of spectral components. So that's the synthesis. And then the spectral component ck can be found by taking an integral over one period of the periodic function between minus pi and pi, therefore, of g of p of x. So we take the function, the periodic function, and we perform an integral times e to the minus I kx. So that, note the difference in sign. So this is a minus here. The synthesis part is positive. That's the way we define it. And the analysis part has this negative part. And here, k is an integer. Just to see what that means, what this means is that if I have any periodic function, g of p, then this integral here tells me, the Fourier analysis tells me, what is the amplitude c of k of the frequency component e to the minus, of the spectral component e to the minus I kx. Okay? That's what this means. And so we are interested in both things, right? So in fact, if I go from the objective, the microscope objective, if I have a sample, the sample contains patterns. Let's look at my shirt here. In real space, you see a pattern that repeats every 2 millimeters or so. You know, it's this checkered pattern. I don't know whether you see it with the resolution of the camera, but you could see a small checkered pattern. And so the microscope objective, if you go to the conjugate plane, the back focal plane, will actually display in that plane the frequency components, right? So there will be, you will see the frequencies of this appear in that plane. And so essentially what you get is the amplitude and the frequencies of the spatial patterns that make up this pattern on my shirt. So what you would expect is you would get spatial frequencies, let's say at position 1 every 2 millimeters. So that would be half. You know, it would be essentially half per millimeter is what that per millimeter would be the spatial frequency that corresponds to this pattern here. It means nothing else than saying the intensity of this pattern changes every 2 millimeters. So that is the spatial frequency. So essentially that is analyzing what the components are. This will become all very clear as we go along, so don't worry if this doesn't make much sense at this point. But by mentioning it already now, hopefully this will this will solidify then once we get to the next part of the lecture. Okay, but so let's now go into our description of what we do in practice. I want you to recall what a phasor is. We remember that a complex number can be written C equals to A plus IB as a real and an imaginary part. And we've already done this, we've already plotted this in Euler notation. You can write the same number with an amplitude and a phase term. And so this A plus IB would be, you would have the real part is A, the complex part is B, and so the length, this could be represented by a vector with a phase phi and a length a, where that's just given by the square root of a squared plus b squared. And you can think of this phase phi here as essentially a frequency at which this vector is rotating in time. So you can think of this of a rotating vector of length a, and it has angular speed phi. And so with that, you can actually get some nice representations of what Fourier synthesis and analysis actually mean. And I will now switch to my computer to show you a demo. So there are two websites that are in the lecture notes. So the first one is this one here for Fourier series. It's this Falstad Fourier applet. So I'm switching to the computer now. So you see this falstad.com Fourier. And so what this does is it's sort of an interactive Java applet. And you can see here, you can see a sine wave that is, let me just see whether I can make sure that you see the whole screen. Yeah. Let's do that again. Yeah, so like this. And so what you see is one sine wave, and so I can now, if I just repeat this, just do this again. Yeah, okay. So I start with the sine wave. So here's a sine wave, and so you see here I can show the sine wave amplitude. So here's the sine wave, and there are other sine waves that I can now put in. I can put, for example, this sine wave in, and so you see the yellow trace is that higher component. It has 3 times the frequency of this component. So you see one component here, another component there, and I can change the amplitude of these individual components by playing with these sliders here. And so each one, you have to take each one of these sine waves and the other and add them with the right phase offset. And if you have the right phase offset between them, you can get this particular result as a function. So let's go, for example, to some waves that you already know how they work. So this is a triangular wave. So the triangular wave will contain a fundamental sine wave. You see here that has the largest amplitude. So actually, for the most part, this triangular wave looks just like a sine wave of this particular frequency here, shown here in yellow. So it already does a good job of mimicking this part. But obviously, the real triangular wave, the red one here, has sharp corners, right? So you need to add some extra bits in there. Let's look. I mean, for example, it needs a bit of this spectral frequency component, right, to be added in. So it will steepen up the slopes and smoothen them out. And there's another component. You see the amplitudes are decreasing, but they are important. If I take those away, if I take these if I take a lot of these components away, let's just do this. Let's see. So if I take a lot of these away, then I'll do a worse and worse. This is not very successful here, but the actual representation, it's hard to see this here, will get worse and worse. I mean, so if I, for example, take this one away, if I put the wrong amplitude in, you can see it's not quite a triangular wave anymore. But you can see by changing amplitudes and by changing, if I change the phase as well, so you see the phase is very important, adding all the sine waves in. So this contains this component, this component, this component, and so on. And so if I don't add phases and frequencies correctly, then I don't get the right periodic function that I want to synthesize. You can then play. So for example, if I want to shift this pattern so that maybe the maximum is not at 0 here, but maybe the maximum shifts around, you can just you put phase shifts in. So by putting each frequency component with a different phase shift, you can now see how the pattern changes. So if I shift more and more and more, you can see down there the phases of these individual sine waves, adding them in, and you know, this would be so this would be sine omega, sine omega, sine 2 omega, sine 3 omega, sine 4 omega, sine 5 omega, and so on. And they are obviously an orthogonal set, right? As a function. So here you see what this integral really means. This sum of ck times e to the I kx is precisely what you see here in action. But if I go back to this phasor description that I just showed you, that's another way. That's another way of thinking about this in complex space. So let's draw this. So if you think of a phasor, so it's going at an angular speed phi. You can see it's rotating around. So from the origin, this vector would just rotate in time. So if I can draw a sine wave, if I let this just move to the left, then you get a perfect sine wave by just having this circle operating at speed y. I can change the amplitude. So if I make this 150, this becomes bigger. If I, you know, so that's what this means. And so now let's add in. So this is radius 100. It goes at speed 1. Let's add in another component. Let's add in another frequency component, e to the I 2 omega. So the speed would be now 2. Let's make it 2 times that, than the original one. And let's make the radius half of that first one. So if I do that, so it's 100 for the first one, 50 for the second one. If I do that now, so I'm adding the first vector, and I'm adding the second vector on top of the first vector. Now, of course, the second vector is rotating around its own origin, right? So when I do this now, you can see how I get a new periodic function as a result of this. So 2 components give you this function, right? And let's add another frequency, and let's make the next one half again, 25, and let's make it 3 times that speed. So let's do that. And so what you see now is you get a different periodic function yet again, right? And so by doing this and adding in more and more components, you can essentially construct any arbitrary periodic function you like. And the Fourier analysis operation gives you the size of these amplitudes. So it would give you 100 for the first frequency, it would give you 50 for the second, it would give you 25 for the third, and so on, right? So by actually performing the integral that I just shown you over one period of this red function here, you would get these components back out. That's what Fourier analysis does for you. Okay, and with that, I switch back to the slides. Not the slides, the writing, the paper writing, and I will just quickly now introduce the next idea, which is the Fourier transform. The Fourier transform now, Fourier transform is extending this concept of synthesizing function to any function, to arbitrary function. So if you do the same operations, you take different frequency components, you add the right phases, and so by doing this with a continuous integral, so including all possible frequencies and all possible phases, you can in fact not just get periodic functions synthesized, you can synthesize any function you want. And the corresponding integral, why that works is if you looked at the animations I just showed you on the computer, I mean, you can kind of imagine that if you just put in any frequency terms, even the ones that are fractional in between, you might consider that perhaps it's possible to synthesize any function like that. And of course, that you can show that that's possible. And the mathematical operation that does that is the Fourier transform. And the Fourier transform can be written as follows. So if I have frequency components e to the ikx, as we just had before, and I multiply them with the amplitudes g of k, so this is called the spectrum of the function, and I integrate between minus infinity and infinity for all these frequencies k, then I can get any function I want synthesized with this. So the difference is that g of k here is in contrast to what we had previously. G of k is a continuous spectrum of frequencies, whereas in the previous case, in the synthesis and analysis case previously, what you have is you had discrete components, omega 2, omega 3, omega 4, omega, and so a discrete or k, 1k, 2k, 3k, whatever the variable is you describe the frequencies with, it's discretely spaced. But here you have a continuous spectrum, it's a continuous integral. And so the inverse of this operation, getting the spectral components g of k, is taking any function and multiplying with e to the minus ikx dx to get the spectral contents back. Okay, so let's just look at this again. Fourier transforms. A function g of x can be synthesized from its frequencies g of k, its frequency spectrum, which is continuous, and you multiply with the spectral components dk. So this is the spectrum, and these are harmonics. And then the spectrum is obtained from any function g of x by integrating over all space g of x e to the minus ikx dx. And you see that these are really symmetric, these two functions. So, so this yields the spectrum, and this is the synthesis part that you get beforehand. And we denote that g of k is the Fourier transform of the real function. So the Fourier transform yields the spectral components, and the inverse Fourier transform, g of x, is given by f of minus 1. So that's how it's written, g of k. Okay? And so if I now I want to start using the following notation. I want to introduce the notation that we have f of x is equal to k over 2 pi. Okay, so k is some dummy frequency, and so k over 2 pi is just a spatial frequency in units per meter. And with that, we can actually start applying the Fourier transform. We can just see what we get. We've already met, when we discussed the rectangular slit, what the diffraction pattern of that slit is. And we found that that gives us a sinc squared function in intensity space. So when we now do this with Fourier transforms, we better get that function back, right? So the Fourier transform. So let's just check that we really get that for the rectangular function. So the Fourier transform of a rectangle. So what is the rectangle? So if I have a function g of x that has amplitude a, so that's the amplitude a over a distance, so if the slit is from minus p over 2, or the rectangle goes from minus p over 2 to p over 2, so it has width p, and it has height a, then let's see what the Fourier transform of that is. So if I have now a rectangle Fourier transform. If I have g of x equals rectangle p of x, and that is equal to a for x smaller equal to p over 2, right? So, and it is equal to 0 otherwise. So this looks like this. So if I have g of x and it goes to a, over its dimensions, and it's 0 outside, then what is the Fourier transform of that? So the Fourier transform of g of x is equal to g of fx, so where we've written fx is equal to k over 2 pi. And that is equal in these with these coordinates. The reason why I've defined f of x like that, it will become apparent in just a minute, is equal to g of x e to the minus I 2 pi fx times x. So that was the original k, remember, dx. Okay, and so what this then does is it so I can then, so if I integrate this, so that is equal to, obviously this integral doesn't extend beyond minus p over 2 and p over 2. So the integral is minus p over 2 and p over 2 because it's 0 outside. Then it's, so g of x is a over that distance. And then I do this e to the minus I 2 pi fx times x dx. And that is equal to, so if I take this out, so that's a over minus I 2 pi fx times e to the minus I pi fx times p minus e. So the 2 goes with, so I put these limits already in, so it's e to the minus I 2 pi p over 2 times fx, so that'll be p, 2 times p over 2, so it's p, and then minus e to the minus plus I pi fx p. Okay, and that is equal to, if I now multiply the front here, just to make this look neater, so I put this in front, and I do pi fx times p, and then I write this as e to the minus plus I pi fx p minus e to the minus I pi fx of p over 2I. So I've taken the minus and reversed those two things here. I've taken these two bits down below here, and that then turns out to be AP over pi fxp sine of pi fxp, which is equal to AP sinc fxp, where this factor pi here doesn't appear in that sinc definition here. This is called, for the engineers, this is called the engineering sinc. So the engineering sinc, so sinc of x, the engineering sinc definition is equal to sine pi x over pi x, right? So you don't write the pi explicitly into the sinc function, and the reason for that is it looks much neater not having the pi there, and it now becomes apparent why this is really useful by writing this in this engineering sinc definition, and you can see that this sinc will be 0. This engineering sinc will be 0 when the term in the brackets becomes pi or minus pi, and it becomes pi or minus pi when fx is 1 over p, right? When fx is 1 over p, so you get pi times 1 over p times p is pi, and then that would be where the first 0 is. So you get this beautifully symmetric situation that for a slit or rectangle of width p, the first 0 appears at 1 over p, and the intensity scales exactly as A times P. So if A is large, then of course the central intensity will be large, and so the broader P is, the integral becomes larger, so that peak will rise. And so you see now why, if I narrow the slits, if P becomes smaller, then 1 over P becomes larger, and that sinc function spreads out. And so you see that these are, this is the frequency spectrum of this rectangle function. That is precisely what we saw with the light diffraction pattern. We illuminate the slit with constant phase light. We get a sinc squared function as the intensity pattern, so we square this thing. And so that is proportional. In amplitude phase, what you get is the exact Fourier transform of the actual rectangular intensity distribution inside the slit. And we saw that by making the slit smaller, the frequency content broadened out, right? So the frequency spectrum, the sinc function, got broader. And that is because the frequency and the real space variable here in x, so this is x here, and this here is fx. They are a Fourier transform pair, and they're inversely related. So the frequency content increases when the real space content decreases. And that now starts to begin to make sense, right? If I want to image a very small object, it contains large frequencies. And so the spectrum will be spread out. And if I can't manage to capture all of that spectrum, my image degrades. And so now you can relate that back to what this means. In real space, we have point spread functions. In the frequency space, we have optical transfer functions. And so both describe kind of the same way, and they're both related by Fourier transforms. They're Fourier transform pairs. And with that, I'll finish this lecture, and I see you in the next one. Thank you.